Hey everybody, and thanks for tuning in to your notes. These are actually our notes titled Area Between Two Curves, and this is actually our first lesson in our new unit, Unit 5. And Unit 5, if you're looking at a broader title here, as you look in this folder where this will be stored, Unit 5 is all about volume of solids with and without revolution. And we won't get into volume today. In order to get to this volume idea, we first have to look at this lesson. So this is just a mini lesson within the chapter, and this is titled Area Between Two Curves. What's interesting is this lesson's going to be really super easy because we have been talking about area trapped under a curve and above the x-axis for quite some time now in our last unit. Well, today we're just going to tweak that slightly and actually talk about area between two curves, and that does not necessarily involve the x-axis. So let's take a look here at this diagram. You see that we do have the x-axis here and we have the y-axis, and we now have two curves coming through. The curve that's kind of on the top here, they're calling f of x. It's a little faint, the print here. And then the curve coming through the bottom is g of x. So you're sort of dealing with two distinct curves. And they have us sectioned off between A and B on the x-axis. And kind of between there, they have this shaded area. So let's look at the questions that follow. It says, examine the diagram above and answer the two questions below. So the first question says, what does the definite integral from a to b of f of x dx find? Well, we know in our studies in the last unit that a definite integral finds the area. I'm just going to write a little note to myself here. It's the area trapped under f of x and above the x-axis. And I say above only because I'm looking at it and it's above the x-axis. It could also be between what's the x-axis and below, but for this one, it's the area trapped under f of x and above the x-axis. So I'm going to kind of color code this. So this in blue, what that would really give us here on this graph is the area trapped between the x-axis from A to B and this curve f of x. So if I color that lightly with blue, it would give me all of this, kind of scooting right over g of x as if it's not even there. By definition, that is what a definite integral finds. Okay, so then the next question says, what does the definite integral from a to b of g of x dx find? And let me grab a different color highlighter here. Well, first let's put it in words. This would find the area trapped under g of x and above the x-axis. Same idea as the f of x graph. I'll make this one pink, so I'm going to highlight this in pink here. And so if I was coloring up above the area trapped under g of x, so here's g of x, let me come through here with pink, under there and above the x-axis, then this would be my pink. So let's remember what we wanted now. We want the area trapped between f of x and g of x. We want this. So if I change the color one last time to green, the area trapped between f of x and g of x would be this section in green. Well, in order to get that, I know I've colored over it, but think about what all the blue was. If you take all the blue and subtract out the pink, you would be left over with the green. So it's pretty simple to find the area between two curves. You just measure from the top curve down to the x-axis, subtract the bottom curve down to the x-axis, and you've got what's trapped between. So I'm going to say that the formula for the area is the definite integral from a to b of the f of x dx, which is all the blue, that was the blue, minus the definite integral from a to b of g of x dx, that was the pink, and that is going to give me the green. Now I can actually write this same expression without doing two definite integral signs. If you think back to Riemann sums, when we did Riemann sums, we took one sigma and we broke it up into 2 or 3 sigmas. Now I'm kind of going backwards. I'm actually going to write this as the definite integral from a to b, and within that one integral symbol, I'm going to just put f of x minus g of x dx. So I took 2 and combined it into 1. And one other thing I'm going to write here is that the f of x, remember, was on the top, and the g of x was on the bottom. And that really is it. That's the formula for area trapped between two curves. It's the definite integral of the top minus the bottom. Okay, now I did do a little side note here because I've been asked this question over the years. The question says, or the statement says, even if g of x dips below the x-axis, the definite integral from a to b of the top minus the bottom will still find the area trapped between f of x and g of x because, and I want to show you why that is. So take a look here. We've got f of x here on the top, and we've got g of x on the bottom, and we have ourselves sectioned off here from a to b. I'm just drawing over that because it's light. Okay, so what I want to do right now is I want to look at, now you can clearly see f of x is right up top. I'm going to make this blue like I did before. So that's all above the x-axis. But g of x is not totally above the x-axis. So let's take a look here. Let's look at this first portion of g of x from here to the x-intercept. Let's kind of highlight that section. So if we were finding the definite integral from, say, a to this x-intercept, let's call that x sub 1. Okay? If we're finding the definite integral just between a and x sub 1, then we would take all of the blue, that's the definite integral from a to x sub 1 of f of x, and then we would have to subtract out the pink, which would be the definite integral from a to x sub 1 of g of x. We would subtract out the pink. And when we take the blue minus the pink, we would get what's trapped between the two, which is the green. So same idea as the last example. So that first portion would be the definite integral from a to x sub 1 of f of x minus g of x dx. Okay. Now, this is the portion I'm really interested in showing you. Say this next intercept here is just x sub 2. Well, now, you might say, okay, well, is this still going to work? Are we still going to take the top minus the bottom to get the total area trapped between these two curves? Well, the answer is yes, but I want to show you in a picture why that is. Okay, if we find, actually, let me write this first. So I'm trying to prove that the definite integral from x sub 1 to x sub 2 of the top minus the bottom is going to indeed give me all this area, including what's underneath. Well, here's how it works. This first part, the definite integral of f of x is going to give me this area, just to the x-axis, all the blue. The pink is going to give me the definite integral for g of x, which is going to be this. So how does that make the green, meaning all of it? Well, if you take a positive and subtract this pink area here, which by definite integral is going to be negative, you're going to be taking a positive minus a negative, and we all know that when you take a positive minus a negative, it turns to a positive because the double negative just becomes positive. So it turns out that even if some of your graph dips below the x-axis, the top minus the bottom, the positive minus the negative, is still going to give you all the green area. And then the last one, if I integrate from x sub 2 to b, again, I'm still going to take the top minus the bottom. And so the top, of course, would just give me all the way from the blue down to the x-axis. Bottom from the pink down to the x-axis. And if we want the area between, we would just simply take them and subtract them. So instead of I did all this done out just to prove to you basically this part in the center here. But really, the shortcut to all of this is simply to go straight through. You can integrate from a to b of the top minus the bottom dx, and that's going to give you the area trapped between the two, even if it goes underneath. Okay, great. So let's get into some examples. So that's all that's left. I think we have 4 examples, so let's get into it. So example 1 says, find the area enclosed by, and they give me 2 functions. So we're going to graph these 2 quadratics. We'll shade in the area trapped between them, and then we'll integrate top minus bottom to find the area. Okay, so y equals, let's start with 4 minus x squared. Y equals 4 minus x squared. Okay, so that has a y-intercept of 4, because when x is 0, y is 4. And if I plug some points in, let's see, when x is 1, y is 3. When x is 2, y is 0. When x is 3, y is negative 5. That's probably about all I have room for. Now I'm going to mirror this on the other side of the y-axis, and we have ourselves a parabola turned downward. Okay, now the second one, y equals x squared plus 2. Same idea. Now my x squared term is positive though, so my parabola is going to face up. I've got a y-intercept of 0, 2. And if I plug points, when x is 1, I'm at 3. When x is 2, I'm at 6. It's about as far as I can go, so I'm going to come to the other side, mirror that, and there's that parabola. Now what I like to do first is let's color in the area trapped between the 2 functions. Let's make that green. This is what we're looking for. And we really want to identify the top and the bottom. So I would say, if you're looking at the top of that green space, that is going to be this quadratic that's turned downward. So this is the top, which makes this guy the bottom. And so when I go to integrate to find my area, I simply do area equals the definite integral. Now I got to find my x boundaries that encompass this green area. So if I kind of trace this down, it looks like -1 to +1. So we're going to go from -1 to 1. And then I'm going to take my top function, 4 minus x squared, and subtract my bottom function, x squared plus 2, and just put with respect to x on the back. Now, you're going to love this. Since we've already studied and proven that we can do fundamental theorem of calculus, in this chapter, I am going to allow you to use your calculator to integrate. So, time saver here. Here we go. I'm going to put this into here by pressing Math 9. I'm going from -1 to 1. Now, I'm going to add an extra set of parentheses here because I don't want to not have enough parentheses. So I'm going to open a parentheses, 4 minus x squared, close, minus x squared plus 2, close, and my dx. Okay, so it looks like I'm getting 2.6 repeating. I'm going to go ahead and call that 2 2/3. So my area is equal to 2 2/3. How easy was that? Okay, let's look at the next one. Find the area of the region enclosed by, and then they give me two graphs. Got a quadratic with a linear. Okay, so I have to start by graphing. So this guy right here has a y-intercept of 2. When x is 1, y is 1. When x is 2, y is -2. When x is 3, y is -7. And I can mirror that on the other side as well. So downward facing parabola, y-intercept of, oops, wrong way. I went over a little bit too far. X him out. I went over a little bit too far with him. Okay, my second equation, y equals -x. Well, that's just linear with the y-intercept at the origin and a slope of -1. So that's just going to kind of cruise this way and this way. So I'll click this. Okay, so it looks like the area that's trapped between them, you got to find that, color it in. It's this green area. So I've got to identify which one's on top and which one's on bottom. So clearly, I hope you can see the top is the quadratic. So this is my top. Bottom, linear. Oh, I was about to write linear. I'm really making mistakes here. This is the bottom. Okay, so now to find the area of the green section, I'm going to do the definite integral from, okay, where is my green bounded on the x-axis? On the left side, -1. On the right side, 2. So we're running from x equals -1 to x equals 2. Of the top, 2 minus x squared minus, watch your signs, the bottom. You have a double negative there. And I'm going to throw that in my calculator. So math 9, -1 to 2. 2 minus x squared minus -x dx. 4.5. Okay, so area is equal to 4.5. 2 to go. Flip it. All right. Find the area of the region in the first quadrant. That's going to be key. Make sure we catch that. First quadrant only. Bounded by y equals √x, the x-axis, and the line y equals x minus 2. Okay. Well, I know what y equals the square root of x looks like. It starts here at 0, 0. 1, 1 is on that graph because the square root of 1 is 1. And then 4, 2 would be the next logical point because the square root of 4 is 2. So that just, we know what that looks like. We've studied that family of functions long enough. The x-axis is just right here. Just highlight over the x-axis. And then this linear equation would come to a b value of down 2 with a slope of 1. So up 1, right 1, up 1, right 1. So that's looking like this. And so the bounded region of those three functions or axes included is going to be right here in the first quadrant because they did say first quadrant. That's why I can't include anything down here because that's not the first quadrant. So it's this green section right here. Okay, now we have to identify the top and the bottom. So it looks to me, if I'm looking at the green, looks to me that the top of that green section right here, that looks like the top, and that goes with the square root of x. And when I go to find the bottom, hold up. I'm seeing two bottoms. Are you seeing what I'm seeing? That looks like the bottom for a little bit, like from 0 to 2. But then from 2 to 4, this looks like the bottom to me. So there's this sort of cutoff here at 2. Top to bottom And then top still stays the root x, but it's got a new bottom. So I would say the x-axis is the bottom from x equals 0 to x equals 2. But then the linear function becomes the bottom from x equals 2 to x equals 4. So no problem, we can handle it. We just have to set up two different areas and add them together. So this is what it'll look like. Area equals the definite integral from 0 to 2 of the square root of x minus, and the x-axis written as an equation is y equals 0, the horizontal line at 0. So minus 0 dx. And to that area, we are going to add the definite integral from 2 to 4. Top remains square root of x, but now the bottom changes to x minus 2. So when I add those together, I should have my area. So I'm going to go to the TI, Math 9, 0 to 2, the square root of x minus 0 dx. And I can do this right away, plus, and then do Math 9 again, 2 to 4, square root of x minus quantity x minus 2. Really important to have those parentheses there so that the minus distributes, and dx. Press enter. And it looks like we've got 3.333 if I go to thousandths. So I'm going to put 3.333. So that is a little twist on the first two examples. And now the last example. This is really going to get interesting. Using right to left integration. Okay, let me speak on that for a second. We've been using top to bottom integration on all of these examples, top to bottom, top to bottom. There's also something called right to left integration. They want us to find the area of the region in the first quadrant bounded by, and they're giving me the same three characteristics here that they gave me up here. So this is going to be the same graph, the same answer, but we're going to complete it in a totally different way. So let's regraph it to start. Y equals root x, we know what that looks like. 0, 0, 1, 1, 4, 2. And the x-axis. And the line y equals x minus 2. And we already know, I'm not even going to draw this other part. We kind of know that that stretches from 2 to 4. So we're looking, again, same exact area. I'll make it green. Now, on a problem like this, because you can see that it indeed has those two bottoms, which can kind of be a pain because you have to do two integrals, you can also look at this as a situation where you have a function on the right, I'll put an R there for right, and a function on the left. And it's 1 to 1. The right-hand side that encompasses this green is just this linear function. And the one on the left that bounds it is the square root function. So it never really brings in the x-axis at all. But here's the thing. When you do right to left integration, everything is about the y-axis. Let me show you why. If you integrate, okay, so what did we say the guy was on the right? The function on the right is the linear function. So this is the right. And it's y equals x minus 2. Okay? If we integrate that function from, now it's all about the y-axis, so from 0 to 2, that would find us the distance, or I'm sorry, not the distance, the area trapped between this function and the y-axis. So it would give us all this blue. And if we integrated from 0 to 2 on the function on the left, which is y equals root x, that would give us the area trapped between this function and the y-axis, which would be this. So if you take all of it minus the pink, bingo, you're left with these leftovers right here, which is the green, originally was the green. So when you set up integration, it's going to look like this. You're going to integrate from a y value to another y value. That's the main difference here, one of the main differences. And you're going to do the right minus the left, dy, with respect to y, because we're now moving up the y-axis. Also, when you write your right and left functions, you have to put them in terms of y, because this measurement, when you measure from the y-axis in this way, this is an x value. This is x equals, not y equals. See, when you measure from the x-axis up, that's a y value. But when you measure from the y-axis over, that's an x equals. So we have to get these two functions, right and left, solved for x in terms of y. That's pretty easy to do. This guy right here, you just add 2 to both sides. So y plus 2 is your x. And for this guy, you just simply square both sides and you get x equals y squared. So here's our final answer. Area equals the definite integral from 0 to 2 up the y-axis, my right-hand function, y plus 2, minus my left-hand function, y squared, dy. And there it is. Now, when I put this in my calculator, you just have to realize you're not going to be typing y's. You can use, even though when you write it, you write y, the calculator doesn't care which variable it is. So we math 9 it, 0 to 2, y plus 2, so x plus 2, minus x squared, dx in this case, but we know it's y. And look at what you get, 3.333. Same exact answer as up top, different method. So keep in mind, if you've got more bottoms or more tops than you care to deal with and you just want a one-to-one situation, you can always go for y integration. All right, that is it. Good luck with your mastery, and thanks for watching.